Hey, welcome. Today, we are going to dive headfirst into a world that pretty much breaks all the rules of our everyday reality. It's a world that's both bizarrely strange and, well, unbelievably powerful. Yep, we're talking about quantum computing.
So let me ask you something right off the bat. We're all kind of used to thinking of quantum effects as, things that happen only at the tiniest subatomic scales, right? But what if that wasn't the whole story? What if all that weirdness could actually break out into our world?
Well, the answer is a huge, resounding yes. In fact, in what was a truly groundbreaking moment for science, the 2025 Nobel Prize in Physics was awarded for this exact thing, proving that quantum phenomena can be observed on a scale we can actually see. This confirms it. The strange rules of the quantum world, they're not just locked away down in the realm of the ultra-small.
Okay, so if this quantum world is all around us, what are the rules of the game? I mean, what does it even mean for something to be quantum?
Get ready, because these rules, they completely turn our common sense upside down. In the quantum realm, nothing is certain until you measure it. It's all just a game of probabilities. And weirder still, the very act of looking at something actually forces it to pick a state. It's the whole idea behind Schrödinger's cat, right? The cat is both alive and dead at the same time until you crack open that box and look. That observer effect, it's fundamental.
So how do we take these totally bizarre rules and build something useful? Well, it all starts with the fundamental building block of a quantum computer. It's time to meet the qubit.
All right, think about it like this. On one hand, you've got the classical bit. It's just a switch, on or off, a 0 or a 1. It's the foundation of literally all modern computing. But then you have the qubit, and it's not a switch. It's an entire sphere of possibilities. It can be a 0, it can be a 1, or, and this is the crucial part, it can be a blend of both at the exact same time.
So the key takeaway is this ability to exist in multiple states at once. It's a property we call superposition. To help you visualize this, physicists use something called the Bloch sphere. Just imagine the qubit is a tiny globe. The North Pole, that's a definite 1. The South Pole is a definite 0. But unlike a simple on-off switch, a qubit state can be any point on the entire surface of that globe. A point near the equator, that might be a 50-50 mix of 0 and 1. A point closer to the North Pole is more likely to be a 1, but still has some chance of being a 0. It's this whole landscape of probability that makes it so incredibly powerful.
And this quote just says it all, doesn't it? It perfectly illustrates the massive difference in power. A bit holds one value. A qubit holds this vast, rich combination of values. A whole tapestry of information woven from pure potential.
So how does this sphere of possibilities actually translate into real computing power? Well, it all comes down to two quantum superpowers that have absolutely no equivalent in our classical world: superposition and entanglement.
We've already touched on superposition. It's this kind of magical state of being in multiple conditions at the same time. A qubit is both 0 and 1, leaning a certain way toward each until that very instant you measure it. The moment you do, that whole sphere of possibilities just collapses into a single definite answer.
And hey, if that sounds confusing, don't worry. There's a brilliant and kind of hilarious analogy for it. Imagine you call Domino's to complain you got the wrong pizza. The person on the phone replies, "Sir, you must understand that our pizza is prepared using advanced quantum technologies. While the courier is on the way, the pizza is in a state of superposition. It is simultaneously a margarita and a pepperoni. It collapses into a specific state only when you open the box." I mean, it's a perfect way to get your head around state collapse.
Now, the other superpower is even weirder, if you can believe it. It's called entanglement. This is where two qubits become linked. Their fates are just tied together. So if you measure 1 and find out it's a 0, you instantly know its entangled partner is a 1, even if that partner is on the other side of the universe. Einstein famously called it spooky action at the distance, and honestly, it's a connection that just completely defies classical physics.
Okay, so we've got these incredible qubits with some serious superpowers. But what's the point, right? Why go through all this trouble when we have ridiculously powerful supercomputers already? And that brings us to the why this all matters part of our explainer.
The truth is, our classical computers, for all their power, they hit a wall. They're built on a very linear, one-thing-at-a-time logic of zeros and ones. So when you face them with problems that have a massive number of variables, like trying to simulate a complex molecule to discover a new drug, or optimizing a global shipping network, they just choke.
For some of these problems, adding just one more variable can literally double the computing time.
This is where the sheer mind-boggling scale of quantum computing becomes clear. So, a classical computer with 300 bits can store, you guessed it, 300 values. But a quantum computer with 300 qubits, thanks to superposition, it can represent 2 to the power of 300 states all at the same time. And that number is what you see here, 2 times 10 to the 90th power. To put that in perspective, that is more states than there are particles in the entire known universe.
And with that immense computational space, we get a true quantum advantage. We can simulate molecules with perfect accuracy to invent new medicines. We can solve optimization problems that are just impossible today, revolutionizing things like logistics and finance. And then there's cryptography. Quantum computers can run things like Shor's algorithm, which is brilliant at one specific thing, finding the prime factors of huge numbers. Why does that matter? Because the security of most of the internet relies on the fact that this is an impossibly hard problem for classical computers. For a quantum computer, it's not. That poses a huge threat to our current digital security, but also a massive opportunity to create new, quantum-proof methods.
Now, I know this might all sound like something from a distant sci-fi movie, but believe me, the quantum future is being built right now, with incredible speed. I mean, just look at this timeline. The pace of development is absolutely breathtaking. In 2019, Google's Sycamore processor claimed quantum supremacy by solving a problem no classical computer could. A year later, China's Zhuzheng did something similar. By 2023, IBM launched a machine with over 400 qubits. And the roadmap for the next few years? It's even more ambitious, with companies aiming for thousands, maybe even tens of thousands of qubits. This isn't science fiction anymore. It is happening. So, the bottom line is, this is going to change everything. We are on the verge of designing new drugs and materials atom by atom, creating financial models that can predict markets with scary accuracy, building unhackable communication networks, and developing AI that could solve some of humanity's biggest challenges, from disease to climate change. And that brings us to a final, pretty mind-bending thought. As we build these incredible machines that literally mirror the fundamental workings of reality, it kind of forces us to ask a profound question. If the universe itself runs on these quantum principles of probability and spooky entanglement, could it be that the universe is a giant quantum computer, constantly calculating its own evolution moment by moment? Something to think about. Thanks so much for joining.